So this is actually from chapter 1. We're talking a little bit about the scientific method. Okay. Like it says, the scientific method is just how we do things in science. It's not rigid. It's very flexible. The diagram for the scientific method is pretty horrendous, but it has 4 characteristics to it. Okay. And I'm going to show you what those things are. Okay, we'll come back to this for a second. The first step in the scientific method is just to make observations. Okay, so some are made with the naked eye. Sometimes we use instrumentation. All the early scientists from the 1700s on used scientific method, and they were not chemists, they weren't biologists, they weren't philosophers, they were natural scientists. And they studied everything together all the time because they didn't know, like, right, what part of it, of the observation was going to be important. So from the time of alchemy on, this is kind of how we've progressed, okay? So that's an observation. It's just what you see, and then you have to learn how to record those things. And we'll talk about recording numbers in observations, okay? Early observations, for example, Anton Lavoisier, this is his wife, who they attribute a lot of his good work to, is actually his wife helping him out in the translations and stuff. He studied combustion of things in closed containers and noticed that, right, the mass of the container and its contents did not change. That's an observation. Make a sealed vessel, you burn stuff in it, you weigh it before and you weigh it after, and nothing changed. From this, actually, we get something much later called the law of conservation of mass. Like, you can't make matter or destroy it. Now, it's not entirely true anymore, right? But for all practical purposes, I take this pen and cut it in half. The 2 halves of the pen weigh the same as the original pen did, minus all the little pieces that fall off. I used to do it with a piece of chalk. With chalk, it was real easy because you just break the chalk in class, and it's like simple explanation. I'd go weigh each half, and everybody would be like, oh, that's cool, conservation of mass. Yeah, anyways, I like chalk. So, from the observation, right, you create a hypothesis. Now, hypothesis is just a tentative explanation of what's going on. What does that mean? Yeah, it's a good guess. Like, you look at what you have, and you try to explain what you see based on what you have. It's a good guess. So Lavoisier said, well, I think, right, combustion involves a combination of a substance with something in the air. What was the something in the air? Well, we know it's oxygen now, right? But he didn't know that at the time. He was the first person to use a balance, a scale, right, to carefully measure what happened during experiments. Well, the first person we have recorded. I'm sure people did it before him. So when you have a hypothesis, you test it by an experiment. So far, what do we have? We have observations. That's the beginning of it. You have a hypothesis, and then you have to have an experiment. Okay, now, when you do an experiment, it's got to be highly controlled. And usually, when we say you do an experiment, you do more than one experiment. You do multiple experiments. And in each experiment, you either try to replicate what you just saw, or you change 1 or 2 variables and see how that affects your experiment. So when I was doing research, one of the things we wanted to know is, we have neurotransmitters. We were measuring dopamine in the rat's brain. And when somebody takes a particular compound like cocaine or what they call dopamine reuptake inhibitors, the ones that are really popular now are the SRIs, the serotonin reuptake inhibitors. Question is, how did they work? We knew the dopamine concentration went up, but we didn't know why it went up. Okay? So it turns out in the studies that we were doing, we took an animal, made a measurement on it, and made one change, right? added the serotonin, dopamine reuptake inhibitors, and looked at the concentration change, and then measured a whole bunch of parameters from that. From that, we could develop a theory. Okay? But we had a hypothesis that there's two possibilities. Of one is the dopamine doesn't go back into the cells anymore, or there's more dopamine being made. And we had to test that. Okay? So that's what we did. So you make a hypothesis, you have to be able to test it. You have to have an experiment, right, that you can test the hypothesis with, that you can ask the question, is this good or bad?
So then you end up with the experiment is built on a way of eliminating different possibilities.
Yeah, and by different possibilities, is like when you make a hypothesis, you actually have a lot of different ideas. Which one's right? So you do an experiment to try to eliminate as many of the wrong things as you can, and then you're just left with a few that maybe can't be distinguished.
And that's how you build.
And then you do another experiment.
Yeah.
Right? You revise your hypothesis, make a new experiment, and try to separate all the different variables out. It goes over and over again. This is why I tell people, it's if you found it on the first try, it wouldn't be called research. Research is because you do it over, like you search, and then you research, and then you research, and you research. For years, right? Okay. Now, people get a little bit confused about this. Okay? From many observations, we can develop what's called a law, or we can develop what's called a theory. Okay? They're two different things. A law tells us what happens when something else happens. If A, then B. Okay? So if I said, to pass this class, you have to get 95% on everything, half the people would leave. That's a law. Maybe not half. So if I said 95% is what you need to pass the class, it's 70%. But if I said half the people will leave, the question would be then, you don't know why they left. You have an idea why they left. But a law doesn't tell you why. It just tells you what's going to happen. Okay? And usually can be boiled down into equations. Okay? So the conservation of mass says in a chemical reaction, matter is neither created or destroyed. So what's the equation? Mass that you start with, right?
Equals the mass.
Yeah. Mass at the start equals mass at the end. I haven't written with this thing in a long time. Yeah, that all gets recorded. It's posted on YouTube. All the stuff I'm blabbling about. As long as the recording still works. All right. Now, a theory, right, doesn't necessarily tell you what's going to happen, but like quantitatively, but explains the why. Yeah, why. And the only difference between a theory and a hypothesis is the theory's just been tested over and over and over, and it's usually bigger. It usually gives the why for every observation. Yeah. Okay. So, and it often predicts behavior well beyond the observations in which they were founded. So it allows us to make more predictions, right? It leads to more theories, right? More experiments. This is why research is research. Lavoisier's law of conservation of mass eventually allowed John Dalton to do atomic theory, okay? Explanation of the composition of matter. What is matter made of? Okay? But all this is experimental, right? You have a theory, you have a law, but even the theory or even laws can be tested. You still can do experiments to try to find flaws in it. Because that's all we get to do in science is to figure out what isn't right. You never really get to say, oh, this is what we've proved. I've proven. Anytime somebody tells me, oh, they proved that a long time ago, I'm like, I don't think so. They have a theory. They have a lot of evidence for it. Proof is Never attainable standard. Okay. All right, so we'll go back. Explains how this all ties together. This is the overarching diagram of what goes on. All right. Starting point is your observations. You can, from your observations, immediately create a law. You could make your own laws, publish those. I think that's what Instagram's for. I don't know. Or Snapchat, right? The way I Snapchat now, right? Not Instagram. I'm like in the 2000s or something. Right. So observations can lead to a hypothesis and then test it, right? Experiments. You either confirm it or you revise it, and you just keep going around in a circle like this, okay? Eventually, the hypothesis becomes so well established that we just call it a theory. And there's not a good line in there. It doesn't say, oh, you know, you did 30 times. That's a theory. You can't say that. You just keep doing it until everybody kind of generally accepts it. Okay? Kind of all nebulous, I know. All right, chapter 2. That was from chapter 1. I will ask you things like, which of the following is an observation? Which of the following is a theory? You can look at there's some look at the problems in the chapter, and that'll help tell you what I might want to know. I'll also try to get a study, like a practice exam up, so you can see the kinds of questions by Friday. We don't have class on Friday, no. But that's the day I get to do stuff, right? That's my day. A lot of stuff to cover. Oh, didn't mean to do that button, sorry. That's the button I meant to do. Okay, measurements and problem solving. Like I said, I stole these slides from my wife, so I'll give her credit. So, a lot of people, I don't know where you guys stand on this stuff. I just wanted to point out some things about data, okay, with this slide. Average global temperature has risen by 0.6 degrees in the last century. Is it exactly 0.6? It's around 0.6. That's the way we would talk about it, right? It's around 0.6 degrees. In scientific terms, what we actually are telling people when we make it 0.6, okay, is it could be 0.5 or it could be 0.7. It's kind of like the average value. It's the digit in which there is a little bit of uncertainty that we don't exactly know what it is. Now we know this, what's to the left of it's 0. But the fluctuation, right, is from 0.5 to 0.7. This is known as the uncertainty of a measurement. So we see 0.6 plus or minus 0.1 degrees Celsius, okay, plus or minus. That's what we mean by it can be from 0.5 to 0.7. Okay. So a couple of things about digits, okay? First of all, we're going to talk a little bit about recording large and small numbers. Now, how many of you remember scientific notation? How many want a refresher? Not the same number? Yeah, okay, good. Scientific notation is decimal between the first 2 digits, okay? Exponent representing powers of 10. All right? So, right, the decimal part is between 1 and 10. It's actually first 2 digits, put the decimal between. Pretty simple format. So how do you convert numbers? Well, if it's a positive exponent, right, you're multiplying it by numbers bigger than 1. So you're multiplying by 1 or bigger than 1, 10, 100, 1,000. It represents orders of magnitude. If the exponent is, that is this exponent here, right? Oh, I should really point like this, actually. That exponent there is negative, then you're multiplying it by numbers that are less than 1, okay? So what does that mean, right? It means that in a number like this, right, this is actually a very small number because this is to the minus 10 power. And so you're multiplying it by 0.0000000 10 times 1.
10 billion?
Yeah, 10 billionth, I guess. Yeah, it's a very small number. Important in science because we deal with such large orders of magnitude difference in numbers that you need to have some way to clearly convey what the value of a number is. And so scientific notation allows us to take really big numbers and record them in a relatively compact format. Okay? We'll see some more examples of this. Okay, so if you want to go from, for example, standard notation, right, to scientific notation, a couple of ways to think about it. Right? It's if you imagine a decimal point here and you move it over 1, 2, 3, right? You're multiplying that number actually by 1,000. That's 1, 0, 0, 0. So that's 10 to the third. So this in scientific notation is that number. A lot of times we just say if it moves to the left, it increases. If it moves to the right, it decreases. Increases means this number is going to be bigger, right? Decreases will mean this number is going to be smaller. So in terms of scientific notation for this other number, right, this decimal that's here, you're moving it over 1, 2, 3, 4 to put it between the first two digits. So that's -4. Now, if you forget, you can say that, what's red lei? I don't know. It's like that. You know what a lei is? The thing, you go to Hawaii, you get to wear the lei. Yeah, right. The exponent decreases. Right, the exponent's decreasing. Left, the exponent increases. Fairly straightforward. So let's practice. That was our national debt in 2013. People like, in the news, this is the number they'll show you, but the scientist doesn't like looking at that. So now we got to figure out what does that number look like in scientific notation. Now, there's a decimal that's here. They're showing one here. So we got to move that decimal over. I know the number part. The number part is just going to be, 1.6342 times 10, and then I just have to figure out what this exponent is. So you just start here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So, dollars.
16 trillion.
It's a lot. Yeah. Bill Gates doesn't even have that much. Oh, you're rounding.
Right.
Right. If you want to, so she asked, is it okay to just say 1.6 times 10 to the 13? It is, depending on what you're trying to do. Okay. No. It depends on what you're trying to do. I'll talk about it. But here, right, if I've given you these digits, these are the numbers you have to record. So you just write it the way you see it. Now, if I say round it to 2 places, then you would round it here. And it would be 1.6. Okay? Just depends on what you're trying to do with the problem. So another one, that number in scientific notation, I hate that it doesn't have a unit, but it doesn't have a unit. So I'm going to go 3.8. Right, 3.8 because that puts the decimal between the first two numbers, not including the zeros. And you shift it over 1, 2, 3, 4, 5. So that's times, so this is 5. So 1, 2, 3, 4, 5. Times 10 to, now which way does that exponent go? Negative, right? So -5. Yeah. Negative, that's a small number, right? Negative goes with small numbers. Positive goes with big numbers.
10 to the minus s.
What's that?
So 10 to the minus s.
Yeah, 10 to the minus, yeah, that's my 5.
Yeah.
All right. Now, that's scientific notation. Now we have to talk about writing numbers with precision. Okay, so this is actually getting to the answer to your question. Right. Some things we count as whole numbers. So these things are known as exact numbers. How many pennies are there?
7.
7? I don't know, 1, 2, 3, 4, 5, 6, 7. Yeah, there's 7 pennies. If anybody gets a different answer, of course, you know that they're wrong because you can clearly see 7 pennies. This number is, in terms of precision, infinitely precise. You know it's 7 because you can count them. Okay? It's like my children. They're 6. Not 5.5. Not 7. Although it's funny because people often think I have more children just because they move around so fast. They can't count them all. Yeah. Now, on the other hand, when you take a gold bar and you weigh it, right, the mass that you get is a 10 gram, it says 10 grams on here. The mass that you get for it depends on how good the measurement device is. So like if I use my kitchen scale, it's going to be 10 with a 1, and I'm not sure that's a 0. Okay? But if I use the analytical balance that's in the laboratories, right, it would give me this as the number, most likely, since we're talking about a gold bar. Okay? All the way out to the 10,000s. Like, but my kitchen balance, it's a 1 times 10 to the 1, because I don't really know that that's a 0. Okay? Actually, I don't use a kitchen balance. I just throw stuff in. I just made that up. See, I didn't lie to you, at least. So, yeah. So this shows I know it to the tens place. This shows I know it to the 10,000s place. That's what we're talking about, precision. Like how closely do you know the number to its actual value? Or how closely do you know the number, I should say? How well resolved is that value? Okay. Now, so when we record numbers as measurements, okay, we record every digit, including the first one that you don't know for sure. Because this could be plus or minus 0.001. So we talked about precision before as plus or minus 0.1. This can be 0.001. So this number could actually be, all right, 45.873 or 45.871.
It falls between the marks. The mark is the 7.
Well, yeah, so the measurement device that was used to get this number would have its last mark probably at this point here.
Is it in hundreds?
In thousandths.
Well, let me
Oh,
see.
sorry, yeah, in hundreds, and you're estimating to thousands.
That's what I'm saying.
Yeah.
The mark is on the hundreds.
Yeah, I'll do examples of that. But the idea is, we know these for sure, and this is the first one we don't know.
You're guessing now.
It's the plus or minus 0.001. What if the number had been 45.9, right? And it was recorded as this instead. Well, then the number, the range in numbers would be 46.0 to 45.8. And you'll notice, right, this is not as precise because it ranges in the tenths, but this one's much more precise because it ranges in the thousandths.
Like that one over there would be like, say, pounds, and just the pounds marks.
Yeah, so if I had a scale, it would have numbers like 44, 45, 46, and I would be guessing at this one. It's close to the 46, but it's not exactly at 46, it's close. All right. We'll see examples when we in the lab, and when I have some examples. Most of the time when you're in a lab, you're using a thermometer. That's like a universal tool for measurement in labs. It's a couple of things that we all have. We all have thermometers. Okay? And I'll show you some examples on a thermometer. Okay. Oh, by the way, that is my kitchen scale.
Yeah, see, it's between the marks. That's what it comes to.
So this balance, okay, has markings every gram or so, right? So how do I know that? Well, this is, right, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And it says grams.
It says gram, so I know it's got gram markings on it. when I tell somebody this is 0.1 something grams, I'm certain of the point, or sorry, if I say this is 1 gram, I'm pretty certain of the 1 gram. I would record that as, okay, hang on. Oh, I changed slides on it, hang on. 1 point, and then I'd have to guess. So how many people say it's 1.5? How many people say it's 1.4? How many people say it's 1.3? 1.2? 1.1? You notice what happened? 1.5, nobody raised a hand. Right? Is it 1.0? Nobody raises a hand on that one. There's some sort of point that we kind of agree, it's probably that. None of you are wrong as long as you're within that decimal, right? So I'm saying that this is 1.2, okay? But if you said 1.1 or 1.3, right, because plus or minus 0.1, we'd all still be in agreement, okay? All right. And of course, just because they put an answer here doesn't mean that's the answer. That's what they say it is, right? And we came up with kind of the same guess just by asking everybody what value they saw. Okay, so this is the mark. These are the marks, and that represents this digit. This line in between represents the uncertain digit. Trying to estimate. Okay? Oh, I hate these. I hated these. Oh my gosh. These kinds of scales, right? They put a pistachio on there. Of course, they put the answer in there too. But this is 0, 1, 2. So those are gram markings, right? So I would say this is 1, and then we could all agree that it says 1, 2. So we all agree that it's 1.2. Where we have to estimate is here, between the 2 and the 3. So if I was looking at that, right, it's not halfway between, right? It's a little bit past. So I think 1.26 is okay. I might have said 1.27, right? But plus or minus that last digit, it's the same. Now, the truth is that dial on the screen is this big. On the device, it's this big. So how do you measure that so precisely? You know, and I'll just tell you guys this. It's okay if you're like me. I pull out my cell phone, I take a picture of it, and I zoom it in. And then I can see what it is and feel fairly confident. I've gotten to the point where I don't have reading glasses, but I probably should get some. Yeah. So I take pictures, I zoom in, get pretty accurate that way. What about this thermometer, right? This might even be today. It's not, but this is your backyard hot tub. In Fresno, you don't need a hot tub to get this temperature. So this is the backyard temperature. Write down what you think it is real quick. So what's the largest decimal? What's the largest digit, I mean? It's the 1, right? Right? It's not past 110, so we know the 0 for sure. And then we know there's a 3. So that part we all get, right? That's 103, because that's 101, 2, and 3. This is the part we're estimating. So if you think about it being halfway in between, it's 103.5. And then we should use a unit, Fahrenheit. All right. So the way we're writing numbers is to demonstrate precision in the number. How well do we know a measurement? So we have a term for this in the sciences. It's called significant figures, okay? So let me explain to you what significant figures are. Just give you the rules, and then we'll practice, okay? All non-zero digits are significant, okay? And interior zeros between two numbers are also significant. So if I look at this measurement, right, there's how many significant figures? 3. So that's 3. And the one on the right, okay, is also 3. Now you're saying, well, that's a 0, right? But if you write it, it means that's the one that you're saying, oh, it's 0.9 or 0.1. Okay? So there's actually 3 significant digits here. Now, why do you say that? Why do I say it's not 5? Because if you convert this to scientific notation, these zeros go away. They only hold places. Okay? This 0, though, because we wrote it and it didn't have to be there, because these had to be there to show the place. We wrote this and it had to be there. That one's included. Okay? So a lot of times when you have this what this call an ambiguous number, ambiguous situation, it's easiest just to convert it into scientific notation. And so you would say 1.10 times 10 to the what? Negative 2. Because I'm dropping this like this. 1, 2. That. Okay. So interior zeros are significant. A lot of times we used to call them trapped zeros. I guess maybe that was lost favorability because people don't like being trapped. But so there's how many here? Significant figures? 5. One's 5. And the one, the 50.1? 3. Okay. In a sense, if you look at these two numbers, right, this one has 5 places to it of precision. This takes a special kind of instrument to be able to measure something that's this big relative to something that's this small. There's a lot of precision in that measurement. Now, trailing zeros, that's the zeros to the right, and those are the ones I was talking about up there, right, are significant if there is a written decimal point. But like I said, this 0 doesn't have to be here. Okay? So the fact that I wrote it means it's important. This 0 didn't have to be here either. Neither did these two in scientific notation, but if you put the decimal here, then it means you're trying to tell people, this is the only weird rule. If there's a decimal, all the zeros to the right are important. Okay? Significant. So this one has 4 significant figures, and this one has 3.
You said all the numbers to the right of the decimal are significant?
All the zeros. If there's a decimal, right, all the zeros to the right of the numbers are part of the significant figures.
Okay, so right to the number, not to the decimal.
Yeah, no, not so. Like all of these are important. Okay. Yeah. Good question. So this one's 4. This one's 3. Okay, so this situation is ambiguous. I have trailing zeros, that means zeros to the right of the number. I don't have a decimal written. Sometimes people say, oh yeah, that's a significant digit. All of these are. Sometimes people say, it's not. So what do? Right, when you're recording the number, write it in scientific notation so people know. Okay, so this one, if this was one significant figure, I would actually write that as... Oops, sorry. I would write that as 5 times 10 to the 4th.
So then your yardstick would be in, say, 10,000s, say, feet or something, and hunks of it like that, and you have 5 of them. Is that right?
You'll have to explain that to me later. That didn't make any sense to me. What? Let's do it. Sorry, we've known each other a while, so say it again.
I'm saying that, you know, what you're doing here is you're applying units, sizes to undefined lengths. That's what the undefined.
Yeah,
Like
in a way we are.
Or,
But if you're talking yardsticks, if it's the yardstick that doesn't have any markings on the inside,
yes, that's what I'm talking about.
then, and you're doing like 100 yards or
Yeah.
1,000
And
yards,
in this case, if you only
It's
have one
good to the
place,
yard.
You have a yardstick that is 10,000, say, feet long, and you're just marking.
Oh,
off
yeah,
there's
this?
5 of them.
Yeah. This would represent a 10, actually, it would represent a 100,000-foot yardstick, and this is halfway through it.
No.
Yeah.
Otherwise, it would be 0.5.
No. What I'm saying is, it's one significant figure.
Oh, that's the guess part, too.
This is the guess. The whole
So
number
it's
is a
100,000.
guess. Yeah, so my yardstick would have to be 100,000 feet long.
That's right, and it's about half of a,
It's about half of it, because I'm so big now.
got it,
Like Fallout 4, you guys can change your size.
yeah.
You can make yourself, sorry, that's a game. You can make yourself as big as you want in the game. So if you need to jump to the top of a mountain, you just make yourself the size of a mountain, you jump, then you make yourself normal size again. Problem is you can't make yourself go through doors when you're that big. Sorry, I only learned this because my sons play, really.
Yeah.
Yeah. They cheat. I don't know how to cheat. I can play the game. I don't know how to all the console stuff. Unless I need ammunition, then I can get more ammunition that way, but yeah. Okay, anyway, sorry. Side point. Yeah, this is a gigantic measuring device, and this digit, the only digit that's significant is the uncertain one. So this value actually goes from 4 times 10 to the 4th to 6 times 10 to the 4th. That's the uncertainty in that value. We're making estimates of 10,000 feet. Okay?
So how many significant figures?
1.
Just one.
Yeah. On the other hand, what if there were 3 significant figures in here? Like you do a calculation, sometimes you come up that has 3 sig figs, right? In order to tell somebody this has 3 sig figs, there's not like a good way to do it. So what we typically do, if it has 3 sig figs in it, we would underline that digit so that people know that's the last significant digit. It's estimated. Or we would write it in scientific notation as this. 5.00 to indicate that it includes this digit as the last significant digit, right? And that's to the hundreds of feet, right? So my yardstick is essentially 1,000 meters, and I'm estimating there. Okay, this number, right? That's 10. Could be probably better expressed as 1 times 10 to the 10. Or 1.0 times 10 to the 10. But if you don't have a decimal, you don't know. So in this class, what we always try to do is convert it over to scientific notation so that we get rid of that guesswork of whether or not the zeros are significant or not. Okay? Yeah. To this?
Yeah, the conversion you've done, you put a 5.0, 5.0, or you
decimal.
Oh, the decimal?
after the decimal, do you put a 0?
You don't have to if it's only one significant figure. If it was 2, you'd put the 0. If it's just 1, you don't even really have to put the decimal
What
there.
happens if you put it?
Then it's there.
Okay.
Yeah. And then I don't get all like excited about it. I was like, oh, it's what it is. Okay, I talked about exact numbers. Those are things you can count. Those are like the pennies, okay, or bicycles. If you're counting the number of bicycles, it would be an exact number because you can count it, okay? Integers, by default, integer values are by default exact numbers. How many significant figures that they have? Doesn't matter. It's infinite. It has as many as you need because it's an integer value, okay? The other kinds of things, and this is a little bit iffier for you guys. I think you guys all understand that integers are exact, okay? Numbers that are parts of equations, that are part of the equation, those can be exact. And some conversion factors are exact. So let me give you an example, okay? Degrees Fahrenheit, we're going to use this one later, is 1.8 times degrees Celsius plus 32. Turns out all the numbers, the 1.8 and the 32, are both exact. Those are defined in that conversion. In fact, that's the reason why you see 1.8 often expressed as 9/5. Because people understand inherently that the 9 is an integer, the 5 is the integer, so the 1.8 has to be exact. The 32 is also exact, right? Now, having said that, some conversion factors are defined quantities. So it turns out, okay, how many of you know how many centimeters are in an inch? 2.54. Yeah, good. 2.54 centimeters equals 1 inch. It turns out that's a definition. They define that to be the case. Everything is actually based on the meter, right? And then they define the inch in terms of centimeters or meters, okay, as 2.54 centimeters is equal to 1 inch. That's the definition. So those are exact numbers as well, just because they're defined that way. Okay. You'll see this is important later when we do calculations. Okay, so let's do it real quickly. Sig figs, what's that first one? 4. Second one? 3. Third one? 2. You don't include these in the sig figs, but they're still there. Okay. So it's just these two. 1 centimeter is 0.01 meters. It's exact. That's the definition of a centimeter. It's 1/100th of a meter, right? So this is exact. So like I said, some conversions, some conversions are exact. 0.500, 3. 2100, 2-ish, maybe. Okay. Based on the fact that there's no decimal here, we'd have to say that it's 2. But again, it's kind of ambiguous depending on how people use that. So we try to avoid it. So we would have expressed this in scientific notation as 2.1 times 10 to the third.
If you wrote that as 2100 with a decimal at the end, then would it be?
2100 with a decimal at the end would have been 4 significant figures. The other option for lab work is just to say 2100 and just go like that. Mark the 1 as the digit that has uncertainty. Okay? Did it get warm in here? Feels warm to me. Maybe because I'm talking a lot. Okay, so we're going to talk about calculations. I'm going a little bit slow. Yes. All right. Okay, so significant figures tell us how precise a number is, how close it is, or how precise the measurement it is. Okay, so when we do calculations with numbers that have precision, right, the result is going to have a certain amount of precision. Okay. So let me say it again. When you do a calculation, okay, with numbers that you've recorded significant figures for, the answer should have significant figures expressed as well. It doesn't suddenly become imprecise or more precise just because you did a calculation. So you have to be able to track the significant figures in the calculations the correct way. Okay? Now, and I'm going to say this, and people are going to have trouble with it all semester. Don't round any numbers in your calculations till the very end. So if you have a 10-step calculation, write a couple of extra digits out all the time until you get to the very end, and then track your significant figures and then round it. Just do the rounding one time, okay? So let's talk a little bit quickly about some of the rules, okay? When you do multiplication and division, the rule is really simple, all right? The answer has the same precision as the number with the least precision that you're using. It can't be the answer, this answer, for example, this is the result your calculator tells you, can't be more precise than the numbers that you used here. So this has 3 significant figures, right? This has 5 significant figures. This has 2. So let me write that out, right? This is 3. This is 5. And this is 2. That means your answer can't be better than 2 significant figures. Okay? Another way to think about it is I know this to about 1%. I know this to about, I don't know, 10,000th of a percent, 1,000th of a percent. But I know this one to about 10%. This digit, if this is 1.1 or 0.09, right? I know it to about 10%. So you can't know this number better than you know this number. So you have to know this one to 2 significant figures. So what you do when you take that number is you say, well, there's 2 significant figures, that's the least. I know that number to that point, and then you round it. So that just becomes 45. And this gets back again to what you were talking about. Can you just write that? Right? Can you just write it as 40? If that's the right sig figs, yeah, then you can do that.
Do you write it as 45 or do you write it 4.5 instead to?
Well, because it doesn't have a 0 here, right? It's not ambiguous, so you could just write it as 45. I generally tell people from between about 1,000 to a 10,000ths, you don't need scientific notation most of the time, just write it. Okay. Here, right, I'd have 4 significant figures here, 3 here. Another way to say it is I know this to the 10,000th, I know this to the hundreds, or thousandths, and I know this to the hundreds. I can't know this number any better in terms of precision. So this is going to be 3 sig figs in the answer. So this is 3. This is 4. This answer has to be done as 3. That's that digit there. Right? So that should be written as 0.96. Then what do I do?
Round it up.
There's a 9 there. Round it up to 6. Okay. By the way, you notice how I stuck a 0 in here? I didn't catch that there wasn't a 0 here. If you're going into any like nursing, sciences, health sciences, always make sure if you have a number like this, put the 0 before the decimal. Okay? They require it. Because did you see how my decimal was real light? Somebody might write this, and then nobody sees this. So you're giving a patient a dose, and you set it on a machine, right? Oh, they need 966 units per hour. Not 0.966 units. Right? That's how people get killed. Yeah.
Does the 45 mean a decimal or does it matter?
Doesn't matter. It could have one or not. You only need it when there's a 0. If it was 40, right, then you should put a decimal. Or scientific notation is 4.0 times, yeah? Then you would be putting a decimal and converting it. I'm going to skip the rounding rules part. I think you all know how to round. There are 2 rules. There's an odd-even rule, and then there's a rule that everybody else knows. If you're going to launch a rocket to Mars, you should know the odd-even rule. But if you're going to be a person, then you should know the other rule, okay? Which is, if it's 5, you round up. If it's less than 5, you round down. You guys remember that rule? Yeah? I'm going to skip it. Okay, so let's do these calculations, and let's round them to the correct number of significant figures. And just for fun, let's figure out the sig figs before we do the calculations. Okay? How many sig figs should be in the first answer? Well, there's 3 here. There's 3 here. 4 here. There's how many here? 1. So the answer should be 1 sig fig. Okay? So we'll do the calculation and then round.
And 2 over on the 3.4.
Yeah, and 2 on the 3.4. So we need 1 sig fig on this one. So I'll whip out my calculator. Actually, somebody else's, but I'm going to steal it for now. Times 0.512 times 1.301 times 0.005. Oh, I get that annoying number. So I'm going to write what I got. 0.00. Tell me if I'm wrong. 3663. It goes on forever. 1 sig fig, that's there.
Do you divide by 3.4?
Oh, did I not divide by 3.4? I did, huh? Okay.
See?
This is why you're supposed to check me. And that's why there's an eraser. I won't edit my mistakes. I'll just do what I'm doing now. Okay, so that becomes 0.001. That's the only, but there's a lot of other stuff here, 0, 7, 7, 5, 3, etc. When you report that number, you round it to 0.001 or 1 times 10 to the minus third.
Because this is what I got. I got to the -4.
Oh. All right, let's take a vote. Is that what other people got? You get -4. You guys should follow along on the calculator. Make sure, I'll double check it later, but the idea is 1 sig fig in the calculation. And it's also that maybe I can't use this calculator, but how many sig figs in this answer? Should have 3, right? Because this one has 4, this one has 6, and this one has 3, so the answer should have 3. Okay, I'll try to be more careful with this one. 4, 5, 6, 2 times 3.9987 divided by 89.5. And then I get this. 0.
That was right. The first one.
Okay, 20382. Oh, you can kind of see the 3 there. Sorry, kind of smashed it together. How many sig figs? 3, right? So I got to round that 3. So the answer should be 0.204. Right? All right, you're doing calculations like a scientist. Okay, addition and subtraction is a little trickier. Has to do with the place, not the number of significant figures. So, let's say you're adding those numbers, right? And you read this number, you know this to the thousandths place, right? This one you know to the thousandths place. So you know that's a 1 or a 0 or a 2, right? And you know that this is a 3 or 2 or 4. And this is what we were talking about before. What's this number here? I don't know, right? I know this is a 3 or a 5, right? But I don't know what this is. So if you're going to add something you don't know to something you do know, the answer is, I don't know.
Very unscientific.
Yeah, so what you have to do when you add these together, you have to look at that last place, okay? That is, you're looking at this last place. You're going to add everything up, but you're only going to keep the result to this place here because that's the only place you know all the numbers, okay? Oh. I watched a lot of baseball games this weekend. I'm a little dehydrated. 5.74 plus 0.823 plus 2.651. Is the decimal even in there? It is. Okay, so I get 9.214. Okay, so I got to write that number down, 9.214. Last significant digit is which one? The 1. Makes sense? You okay? She had this grimace on her face, but I think she was just sneezing or trying not to sneeze. Yeah. And now that I've pointed it out, it's probably really embarrassing. We all do those things. So 9.21. So we're going to do subtraction. The rule applies for subtraction too, right? I know this is an 8. I know that's a 9. What's this? I don't know. I don't know what that is either. Now, when you do the math, you just assume they're zeros. Okay, you don't stop. It doesn't stop you from doing the math. But we're going to round this one to the tenths place. As we're going to round it to this point here. So I got to write this out as 4.8 minus 3.965, and I get 1.105.
you said you had the 0 to do the math.
You gotta have the 0 in there to do the math,
Yes.
but you don't keep it as a significant figure. And so now I've got to round this one to the 10th, so this is just gonna be 1.1. Gotta make my decimals bigger somehow. All right? Okay.
Is that 1.1?
I don't know, did I-
Is that what you got there?
Yeah, is that what I got?
Oh, okay.
Did I subtract wrong?
No, but I mean, it's not too significant, well, it is too significant.
Let's see, 4.8
The point is, it's
minus
one
3.965. Oh, I don't know how I got that number. Oh, stop me before I hurt things. Okay, cross that out. Concept is still the same, but I got, what, 0.835?
Yes.
0.835. And then I'm still keeping it to the tenths, right? So that's this, and so it's going to be 0.8. All right, better?
Yeah.
Okay. Sorry about the confusion on the calculations.
Actually, I got .8035. Is it wrong?
I don't know. 8 through 5?
Oh,
Yeah.
I see what it is.
Okay, good.
I hit the 9 twice. That's one nice thing about these, you can see where you've been.
Us two old guys were screwing it all up. These guys all got it. Go ahead. Should have done it on my phone. Just ask Siri. Yeah.
In the example to the right, assuming the number after the 8 was larger than 5, would it?
It would have been 9. Yeah. Same rule you round up.
So if it's the 3 is 5, you round it up to 0.9?
If it had been 8.5, then you would have gone to 0.9. Yeah. Okay. So just a little side note. I'm going to actually skip this slide. I'll talk about it here, though. Let me talk about this one. You notice this was 2 sig figs, and this was 4, right? And the answer had 1. So when you do addition and subtraction, sometimes sig figs change. When you subtract, the general problem is you lose significant figures. And when you add, because you can add tens places, right, you can gain significant figures. This is why averaging works, is when you average a whole bunch of numbers together, you're really adding them all up, and you increase the amount that you know by adding the numbers and then dividing by the total. Okay, we'll talk more about that in lab when we do the practical examples. Okay, skip a couple slides. So what happens if it involves both multiplication, division, addition, subtraction? Then you do that PEMDA, yeah, whatever it is, right? Parentheses, right? Multiplication, division, addition, subtraction. You go through that. You just do that, and you track the significant figures all the way through, right? You do the calculation, and then you round at the end. So let's just look at a couple of examples, okay? So I'm going to do parentheses first, right? So I'm going to take 782. You guys might want to check me on this. 782.3 minus 451.88. So I get 330. .42. Now, you notice I only know this number to the tenths place. That means when I do the subtraction, I don't really know the hundredths, I only know the tenths. So the last significant digit in that number is the 4. That makes sense? I didn't line it all up, but because I know this number to the tenths, I know I need to know this number to the tenths. Now this number has 4 sig figs in it. So I'm going to multiply it times 3.897. And I'm going to get a number where I can't even see the decimal point. It's a big number, huh? 2, 87
.64.
point 6467
674.
674
No, that was right.
64674. There we go.
Correct.
It's like I can barely see the decimal on this one. Okay.
Yeah.
Now I know this one to 4 sig figs. I know this to 4 sig figs. So this answer, 4 sig figs, I'm gonna round it to the 7. Okay. Place. So that becomes 1, 2, 8, 8. Okay. I did this calculation in tracked sig figs, right? And then I multiplied it together. I got an answer. Right? Same answer as you should have all gotten even before you knew significant figures. And then I rounded it. So do the same thing with this one, right? 4.58 divided by 1.239. Oh, I keep hitting buttons as I'm holding this. I get 111? No, what do I get? Oh, see, I think that's what's been happening. I've been hitting the equals thing with my iPad as I do. So 4.58 divided by 1.239.
3.69.
Yeah, 3.6965. Now, this is multiplication division, right? In the parentheses, right? So, how many sig figs in this answer? 3. I'm going to mark it like that so I know. You notice I wrote a couple of extras. And now I'm going to subtract 0.578. So I'm going to end up with 3.1185, et cetera, et cetera, et cetera. Okay. So I know this one to no, it's 3 sig figs. But remember, now I'm subtracting these two out, right? So I know this one to the 100th.
All decimals.
Yeah, and so you see what's happening here? Here I did a division and I got this as an answer. Now I'm subtracting. When I subtract these two, I keep track of places.
Of the decimals.
Yeah, the decimals. So this is to the
Not sig
100th.
figs, but the decimals.
Yeah,
Yeah.
to the 100th, right? So this is going to have to be, when I subtract it, this answer needs to be rounded to the 100th and not worry about like how many sig figs.
That's right.
Right. So this one's going to get rounded to, oops, here. And so that becomes 3.8, oh sorry, 3.12. Tomorrow's study guide is all about this. But it's on the homework.
Let's do tomorrow.
Yeah, due tomorrow. So units of measurements. My wife wrote this example. I don't even know what she was trying to say. So read that sentence. When my son was 7, so that kind of makes sense, he walked 3, and when he was 4, he could throw his baseball 8 and tell us that his school was 5 away. Right? Does that make any sense to anyone except my wife? Yeah, there's no units of measurement. Was he 7? Or was he 7 years old and he walked 3 miles? Or was he 7 months old and walked 3 feet? Actually, he was 7 months old and he walked 3 feet. Right, we were really busy with our first child. He walked really early. And when he was 4 years old, right, he could throw a baseball 8 feet. Those kinds. We're missing things, right? The things that we're missing are called units. It describes the number. So every number that we have in this class has a number, numeric part, and a unit. And the unit tells you what that number represents. Okay? So the two common systems that we use are the English system. The English don't use it, but we do.
That's right, that's what cracks me up.
Although a lot of the older English people I know, that's all they use still. Right? But the English system, inches, right, feet, pounds, ounces, right? In the metric system, it's kilograms or grams, right? What else? Meters, liters for volume, okay. And it turns out in the metric system, all these numbers, they're all interrelated in like logical ways. In the English system, it's, yeah, metric system is multiples of 10. English system is just, I think, whatever they decided to do. Right? Okay, so, yeah. Right, so there was, in 1999, this is a great story, $94 million orbiter got lost because they didn't tell each other what units they were doing. Instead of launching the orbiter around Mars, it just ran into it because they didn't get the unit conversions correct.
There was two separate deals working on it. One of them was using the one and one was using the other. They didn't
Yeah. They didn't communicate. This happened more than once. There was one time where an airline, a jet, ran out of fuel because they didn't calculate the conversion correctly. So, they load the jet just enough fuel to get where they're supposed to get to. Well, they didn't convert it correctly, and because they didn't convert it correctly, didn't use the right unit conversion, the jet ran out of fuel before it got there. So they had to land. Fortunately, it wasn't over the Atlantic. Okay. So we use this international system of units, SI units. The units that we prefer to use are meters, kilograms, or grams, okay? Seconds for time and Kelvin for temperature. Okay, we're going to spend more time on Kelvin later, but Kelvin is very closely related to the Celsius scale. Okay?
How come they call it, wasn't that the same as centimeters? I mean,
What?
excuse me, never mind.
Okay, I will never mind.
Okay.
So a meter is a little bit longer than a yard. It was defined as the distance light travels in this much of a second. I don't know why they came up with that. Originally was defined as that. Now it's based on oscillations of an atom. Yeah, it gets crazier and crazier. But a meter literally is, on rough estimates, that. And on the other side we have inches. Now how many inches in a yard?
36?
36, right? So if I flip this over, that's a meter. That's a little over 39 inches.
39, 37.
Right? 39 point, I can't read it.
I think it's 37, or 34.
I don't
See
know.
it both ways.
Let's see, it's right here. This is a meter, right? It's gotta be 39 something, yeah. Yeah, it's right there, so that's what a meter is, okay? Yeah, it's a meter stick, it's not a yardstick. Most classrooms these days don't have yardsticks, they have meter sticks.
Is that right?
Yeah. Mr. Balo, when he sees a yardstick in class, he breaks it in half, throws it away. Yeah, I keep it away from him. Okay. A kilogram is a little more than 2 pounds. I'm just telling you these things so you guys get an idea of what they are. Kilogram is actually about 2.2 pounds, but it's about 2 pounds. What would 2 pounds be roughly? Well, if you go to the store and you buy 2 packs of butter, that's 2 pounds. That's around a kilogram, okay? So kilogram is what we use to do what's called mass, okay? And mass is the measure of the amount of matter that's in an object. So we have two concepts. There's mass, and what's the other one you guys? Weight, okay? Weight has to do with gravity. Mass is inherently how much material there is, how much matter there is in an object. So if I go from ground level, right? And I go to outer space, my weight changes. I become weightless in space, okay? But my mass doesn't. I will not tell you my mass. But my mass on the Earth and my mass in space is the same. The way that you kind of know that is, can you imagine if you're in space and you have to stop a ship that's trying to dock, right? It doesn't have any weight, it has 0 weight. But if you tried to stop it, it would crush you. Because it weighs thousands of pounds on Earth, it has lots of mass, kilograms, thousands of kilograms of mass. You try to stop it, you'll feel the force of the mass as it tries to crush you against the ship. Okay? Yeah, it's from inertia. That's actually how they measure a lot of these things. Okay, so Common unit of mass is the gram. There are 1,000 grams in a kilogram. Kilo, K, is what we call a prefix. Kilo stands for 10 to the third. Okay. So a kilogram or a kilometer, right, or kilometer as we'd say it, right? But a kilometer would be 1,000 meters. For time, we use the second. It's based on the oscillations in cesium-133, right? There's people that have time enough to do this measurement, right? That's how we do our atomic clocks, so we measure oscillations in atoms. Okay, so let's go into the prefix multipliers real quickly. There's a bunch of these you'll have to memorize, okay? So a kilogram is 1,000 meters. I already said that. It's 10 to the third. Oops. I'll just show you a bunch of them here in a second. But you would write it as 10 to the third meters. Or 1,000 meters. My internet connection's getting a little iffy here. This is what a whole bunch of them look like. And this is what I want you to know, okay? I'm going to mark it on the side here. From nano, like nanotechnology, right? To giga. That's that whole range here. So if I say I have a nanometer, nano is 10 to the minus 9. Like in decimal format, it looks horrible. It looks like that. It's 10 to the minus 9. That's a billionth of a meter. So like when we talk nanotechnology, we're talking about things that are billionth of a meter. So if you imagine this is a meter, you don't have to imagine that is a meter. 1,000th of a meter is just one of the little divisions that you can kind of see the gray line down here. That's one of those divisions is a 1,000th. If you took that and you expanded it 1,000 times, so it was this length, and then you took the next subdivision and you expanded that 1,000, then you would be on the nanometer scale, okay? Or you could imagine this thing 1 billion times longer, and this would represent 1 nanometer, okay? It's a very small, small measurement. It's near the dimensions of atoms, which are very small. Other notable ones are milli. We use millimeters, right, all the time. And then centimeters is used all the time as well. So that's what all these prefixes mean, and each one has a numeric representation. It's actually not hard to do if you just ignore these two middle ones, because it's 9, 6, 3, 3, 6, 9, but to the negative. So all in powers of 3, right, factors of 1,000, except for centi and deci, which represent, tenths and hundredths. So if I say I have a centimeter, right, there's 100 centimeters in a meter, because a centi means 1/100th of a meter.
Like a cent for a dollar.
Yeah, and just like a dollar is made up of 100 cents, right? Cents literally means 100th of a dollar. Okay. So let's say you have, this is the polio virus, this is dimensions of the polio virus, it's 2.8 times 10 to the minus 8 meters. People don't like writing this because it's really hard to interpret this as a value, right? So what they like to do is they like to use a prefixed meter to express that value more clearly to people, okay? So which one of these would be the best unit to measure it in? Well, this is what, 10 to the minus 8, right? So let me do this. Write it out. 2.8 times 10 to the minus 8 meters. Now, nano is 10 to the minus 9, and micro is 10 to the minus 6, okay? So a couple of ways you can do this. Remember what I said before, if you move the decimal right, right, the exponent increases. And if I move the decimal left, the exponent decreases. So that's the red lay part. If I take 2.8 and I move the decimal from here to here, I'm moving it to the left, right? Then it becomes 0.28 times 10 to the minus, let's see, left is increases, 10 to the minus 7, right?
That's right, see,
Right, so I can go a little bit more.
that's right.
I could go a little bit farther. If I go one more, like this, right, this becomes 0.028 times 10 to the minus 6. And now this is a micro. So you could actually report this number as 0.028 micrometers. Or you could go the other way, right? So if I go to the right on this number, and I take it this way one, then the exponent decreases, right? So I'm going to take 2.8 times 10 to the minus 8. I'm going to move it one this way. And I get 28 times 10 to the minus 9 meters. 10 to the minus 9 is a nano, right? So this is just 28 nanometers. So this is a much easier or a nicer way to express this number, right, than using all the scientific notation and stuff. But you have to be good with scientific notation and converting back and forth between the two. Now, I just picked the one that was hardest first, that made the wrong answer, so I could actually do it, right? I would have looked at this decimal and say, oh, well, it's probably closer to 10 to the minus, this is closer to 10 to the minus 9. I would have made it 10 to the minus 9, and then use that prefix, okay? So the 8, that's this value here, is closest to the nano prefix, so I would have used nano as the prefix. And then shifted it that way to get that. Okay. A little behind already. That's because I had to do all that syllabus stuff before. So this is what we're going to do. So there's a bunch of unit conversion stuff. I don't know where the homework stops. I will post which problem to stop at tonight. Okay? But go ahead if you've already, some of you have already done it because you already read the whole chapter. But I'll post tonight on Blackboard. Hey, go up to this problem, and then you can do the rest of them in the lab tomorrow, because tomorrow we're going to do a worksheet and a lab, and we got to make sure, for sure, we get the worksheet done, because it's all of this stuff. And then you can finish your homework, and then we'll start the lab if we have time. Okay? Huh? Yeah, there's one in the experiment. Just look it up. Do you want me? I'll show you here.